Hello, my physics friends again. Here you are with Miss Parent. We are going to do some position time graph examples. So let's look at a couple of these. We won't look at all of them, but just a few. So sometimes it gives you a conceptual example and it asks you to draw what a position time graph might look like. So let's look at number 2 here and number 3. So number 2 reads that car A is stopped at a traffic light. The light turns green and starts up. Just as it does, car B passes it going a steady velocity. Eventually, car A passes car B. Sketch, on one graph, the motion of car A and car B. Okay, well I'm going to draw just a basic, simple T and D, and then I'm going to use 2 different colored pens for each car. So I'm going to do car A in red and car B in blue. Okay, so I'm going to start with car B, and I'm going to start with car B because car B is the easier car to draw. It tells me that car B passes car A and it's going a steady velocity, a constant velocity, which means that for car B, it's just going to be one nice straight slope. Now car A is a little bit trickier. It says, let's write car B. Car A says, car A is stopped at a traffic light to start, which means that, and if car B passes it when the light turns green, that means car A must start ahead of car B. So I'm going to start car A here, and I'm going to draw a horizontal line because it's stopped at a traffic light. And at the moment where car B passes car A starts to move. And it does say that A eventually passes car B, so that means that I'm going to have a steeper slope on my car A. And at this point here is where car A passes car B. Next example states that a car is traveling along a flat road when it passes an unmarked police car beside the road. The police car accelerates, overtakes the speeding car, passes it, and signals it to stop. Sketch the position versus time graph showing the motion of both cars. So here is my axes. And let's think about which one is easier to draw. Is the police car easier to draw, or is the speeding car easier to draw? Well, it looks like the speeding car is easier to draw because the police car does more changes of its motion. It's stopped, it accelerates, or it speeds up, it passes the speeding car, and then it signals it to stop. So I'm going to take my speeding car and I'm going to make it pink. And I'm going to just draw a, again, similar to car B, a straight, constant speed, but at a high slope because he's speeding. And then my police car, I'm going to make green. And it says that the speeding car passes the unmarked police car that's stopped. It's parked beside the road. So my police car starts not moving. And then when it gets past, the police car then accelerates, which means he speeds up because I'm changing his slope so that he can catch up to the speeding car, pass it, and then signal it to stop. So then they both stop and have zero motion at the end. That's a tricky one. I also kind of put that in a very small position time graph. You could make it spread out a little bit more. Let's look at question number 4 here. This is more of an analysis of a position time graph, and it's more of a conceptual analysis. So this is saying the position time graph shows the motion of a young child just learning to walk. Use it to answer the following questions. So where is the child traveling the fastest? So that would be the area where the slope is the steepest. So let's label these sections. So I'm going to label that A, B, C, D, E, F, and then this curved part here, I'm going to label that G. So where is the slope the steepest? Well, it's definitely steep over here in G, and it's also pretty steep here in E. So I'm going to say E and G. Where is the child traveling the slowest and still moving? So that's looking for the most gradual slope. And that looks like section C here, the most gradual slope. Where is the child traveling forward or away from its starting position? So that would be, if the starting position is here, A and E are where they're traveling forward. And where would the child be traveling backwards? So that means he changed directions, or she changed directions. They were moving forward, and then they just walked backwards. Same thing as turning around. So that would be in section C and in section G. And one more example that we're going to do is more of a mathematical example. And that's this example here. This graph shows the position of a scared rabbit running from a hungry dog. Oh no! Use the graph to answer the following questions. So this one says, how fast is the rabbit traveling during the first 3 seconds of running? This is asking me to find how fast. So I need to look at the slope. So for A, I'm going to use the slope to figure out how fast. So the slope is a change in y over a change in x. And so that would be y2 minus y1 over x2 minus x1. And if I look at my coordinate points, 3 seconds, I'm at 3, 8. So this is 3, 8. And over here, I'm at 0, 2. So 3 minus 2 is 1, and 8 minus 0 is 8. So 1 over 8, or 1/8 meters per second. You could do the division. If you wanted to do that division, you would get 0.125 meters per second. B says, how far does the rabbit run from 4 to 8 seconds? Well, it's asking to see how far he went. So at 4 seconds, he starts here at 8 meters. And at 8 seconds, he's here at -4 meters. So remember, the negative on position doesn't mean less distance. It means direction. And so here, well, I've gone 8 meters to 0. And then he continues for 4 more meters past 0. So 8 meters plus 4 meters, 12 meters. C is asking how fast is the rabbit traveling during that time period. So again, that's the slope. So then this would be -4, 8, -4, 8 minus, my y is +8 here, and I'm at 4 seconds here. So this is equal to -12 over 4, which is -3 meters per second. Then D is asking us to figure out when is the rabbit traveling the fastest. It's not asking me to figure out the time or the speed. It's asking when. So it's looking for a time interval. And in that case, I can just look qualitatively at the steepest slope. And that looks like it's right here from 9 seconds to 10 seconds. Because it definitely covers 10 meters in 1 second. So the when the rabbit is traveling the fastest is from 9 seconds to 10 seconds. And E says, when does the rabbit rest? And that's when the slope is horizontal or there's no slope, because that represents no motion. So that would be between 3 seconds to 4 seconds, and then again from 8 seconds to 9 seconds. And that's how you can analyze position time graphs.